Let's look at this picture again, right? So we have sequence and then we take sums of first n entries or n terms of the sequence, and we get some Sn, which is partial sums, and then we consider the limit when n approaches infinity. We get S infinity in here, in very informal, and the series sum from 1 to infinity of ai is nothing but the limit of Sn when n approaches infinity. Does that make sense? So we already define series using sequence. And the convergence of series is understood as, the limit, as, the existence of the limit of these partial sums, right? We have sequence of partial sums. Don't forget that. Look at this. So we have sequence of partial sum. I write here. Sequence of partial sums. Okay. So the series converges if the sequence of partial sums has a finite limit. Otherwise, the sequence diverges. Okay, so we determine the convergence of sequence using limits. And of course, using this definition, you will see that we can find the sum, right? We can find this sum using the limit of sequence of partial sums. Okay, so in this section, we are interested in the convergence of sequence of series. Sometimes we just need to determine if a series converges or diverges. And sometimes, if it is possible, so we can find the sum of a series. Okay, so let's consider the following example. Sum I from 1, let's say n from 1 to infinity, 1 over 2 to the n. So if we spread this out, we have 1 over 2 is for n equal to 1, plus 1 over 2 square, plus 1 over 2 cubed, plus so on, plus 1 over 2 to the n, plus so on. The term 1 over 2 to n is called the general term, right, of the series. Okay. Now, let's determine whether this series converges or diverges. And if it is possible, let's find the sum of this. Okay? So look at this. If we write in the form of partial sums, S1 is 1 over 2. Right? S2 is 1 over 2 plus 1 over 2 squared. You have S3 equal to 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed. So let's sum them up. You get this 3 over 4, right? And in here, you get 7 over 8. All right? And so on, Sn, which is 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed plus so on plus 1 over 2 to the n. All right, of course, if you can guess the general term, that would be perfect. But in my opinion, this is extremely difficult. This is extremely difficult to guess the form of the general term of a series. So we know Sn, right? Let's try to find this sum. All right, so if I factor 1 over 2 out, I will have the following one. 1 plus 1 over 2 plus 1 over 2 square, right? Plus so on plus 1 over 2 to n minus 1. Is it correct? And if we pay attention on this form, you can see the following one. This is nothing but Sn minus 1 over 2 to the n. Is it correct? Because by the definition, n is sum of these terms, 1 over 2 plus 1 over 2 squared and so on, 1 over 2 to the n. But here, you don't have 1 over 2 to the n, right? So basically, if you subtract from Sn 1 over 2 to the n, you get this term. Is that correct? So I can write the following equation. Sn equal to 1 over 2, 1 plus Sn minus 1 over 2 to the n. So you have some equation of Sn. Is that right? So using this, you can solve for Sn. You get the general term of Sn. Let me write this. You have 1 over 2 plus 1 over 2 Sn. Okay, let's do this. Let's multiply both sides by 2. Okay, so I have 2 Sn in here equal to 1 plus Sn minus 1 over 2 to the n. Okay, and then you simplify 1 Sn because here you have 2 Sn, here you have 1 Sn. You have Sn equal to 1 minus 1 over 2 to the n. Or you can write in the following form, 2 to the n minus 1 over 2 to the n. All right, so now you see, you may verify that, for example, when n is equal to 1, n is equal to 1, so S1 equal to 2 to 1 minus 1 over 2 to 1, which is 1 over 2. Perfect. Here is n equal to 2. You have S2 equal to 2 square minus 1 over 2 square. That is 3 over 4. It's also good, right? So let's say n equal to 3. So S3 is equal to, according to this formula, you get 2 cubed minus 1 over 2 cubed, which is 7 over 8. So it looks good, right? All right, so general term is, we just file this as n equal to 2 to the n minus 1 over 2 to the n. So this is your sequence, right? The sequence of partial sums. Is that correct? So you can show the convergence of series using this. Okay, so I can write like this. The series n from 1 to infinity, 1 over 2 to the n is equal to the limit of 2 to the n minus 1 over 2 to the n approaches infinity. You have the limit of this guy, right? So I think it's pretty simple, right? You use similarity because you might ignore 1 on the top. So this limit is equal to limit of 2n over 2 to the n and infinity. So you have 1. That means sum 1 over 2n and from 1 to infinity is just 1. So that means our series converges and equal to 1. Okay, so look at this one more time, right? In this example, we found the sum of a series using the sequence of partial sums. And of course, sometimes we are successful to find the general term in here, but sometimes it is not easy at all. Okay, let's move to the second example. Let's consider the following series: 1 over n minus 1 over n plus 1, n from 1 to infinity. In this case, an general term is 1 over n minus 1 over n plus 1. So let's determine the convergence and the sum of this sequence if possible. Okay, look at this. This is my an, right? Equal to 1 over n minus 1 over n plus 1. So if we pay attention, you would think that if you move from an to an plus 1, so what is that? That is 1 over n plus 1 minus 1 over n plus 2. Is that correct? And then when you sum them up, you see these two terms will be cancelled out. These two terms will be cancelled out. So basically, based on this observation, you may write a sequence, and you get a very simple one. You may write the sequence, the series like this. Sorry, the series. So you have A1 plus A2 plus so on plus AN and so on. Okay, and then you can see the following one. What is A1? A1 is 1 over 1 minus 1 over 2 plus A2 is 1 over 2 minus 1 over 3 plus A so on, okay, and then plus AN is 1 over n minus 1 over n plus 1 and so on. And then you can see like this. This will be cancelled out, this will be cancelled out, and everything will be cancelled out, right? In here, everything in between will be cancelled out. So at the end, you get just 1 minus 1 over n plus 1 and so on. And of course, if you continue this, right? So 1 over n plus 1 will be cancelled out. Does that make sense? So if I write this as a partial sums, I will have the following one. S1 is 1 over 1 minus 1 over 2. Okay. S2 is 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3. And that is 1 minus 1 over 3. Okay. And so on, Sn equal to 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus so on plus 1 over n minus 1 over n minus plus 1. So as we have seen here, right, in here, all terms in here will be cancelled out. So basically, Sn is equal to 1 minus 1 over n plus 1, which is very good. And we can see that the limit of Sn when n approaches infinity is just equal to 1, right? Because the limit of 1 over n plus 1 is 0. You see that? So since the limit of the sequence of partial sums exists and equal to 1, the original series converges and equal to 1. And that is the conclusion. And of course, let's write converse. Okay, so two series converge, which is good. Now let's consider a very simple one, okay, which is divergence. So here's my series, -1 to the n, and from 1 to infinity. This is quite interesting, series. So if you write this down, right, what is S1? S1 is -1. S2 is -1 plus 1 is 0, right? S3 is -1 plus 1, and then minus 1 is -1. S4 is, again, you might guess that is just 0. So basically, okay, Sn is, I can, okay, let me write this. -1 to 1 plus -1 to 2 plus so on plus -1 to the n. And of course, it really depends on the n, right? If n is an even number, Sn is 0. N is even. And if n is odd, then the sum is -1. So this says that, the sequence of partial sum Sn does not have limit. Does that make sense? Does not have limit. The limit Sn and approaches infinity does not exist. So this guy just converges. Now let's talk about geometric series, which is one of the most important objects in this theory. For a constant A, and A is constant, okay, and R such that absolute of R less than 1, we have the following formula. Sum of n from 0 to infinity, a r n equal to a over 1 minus r. All right, so let's talk about this formula. Firstly, index n runs from 0 to infinity. Okay, so usually, when we consider a series, and when we are interested in only convergence of series, that's okay. The index 0 does not matter, because you add or subtract a constant, a finite number, right? You don't change anything about the convergence of the series. But if you want to find an exact sum of a series, so you need to pay attention on that. And in this case, this formula works for index from 0 to infinity. We can prove this very easily. You can see that in the textbook. It's not a big deal. Okay, but again, right, this is very simple but extremely useful. Okay, so you have two constant a and r in here. You consider a r to the n, that is a over 1 minus r. Only happens when absolute r less than or equal to 1. So what happens if absolute of r greater than or equal to 1? In this case, this series diverges. Okay, don't forget that. So this is okay. We need to know this situation, right? Because sometimes you see that. But if you want to see the formula, yes, right here. And that works only for the case when absolute are less than 1. Okay, so let's go back to the previous example. 1 over 2 to the n, and from 1 to infinity. So if you remember, we found that actually the sum is equal to 1. You see this? The sum is equal to 1. Now let's use the formula of geometric series to prove that the sum actually is 1. Okay, but we have to pay attention on this. Here the index runs from 1 to infinity, and here the index runs from 0 to infinity. So if you want to use the formula of geometric series, you need to add and subtract the terms corresponding to n equal to 0. Does that make sense? So I write the following one. N from 0 to infinity, 1 over 2 to the n, equal to n from 0 to infinity, 1 over 2, everything to the n. Is that correct? So according to the formula, a in this case is 1, r is 1 over 2. So you have 1 over 1 minus 1 over 2, which is 1 over 1 over 2. The answer is 2. But the 2 is for this series, not for this one, because you have n equal to 0 in here. So from here, I have series from when n runs from 1 to infinity, 1 over 2 to the n, that is equal to series 1 over 2 to the n, and from 0 to infinity, right? Minus 1 over 2 to 0. Is that correct? So you exclude the very first term, right? We say the 0 term. Is that correct? So basically that is 2 minus 1, which is 1. You see, that's how geometric series works. Okay, so let's consider another example. We have the following series: 3 over 2, let's say 3n to 2n, and from 0 to infinity. Okay, so you might rewrite this series as 3 over 2 to the n, and from 0 to infinity. In this case, a is 1 and r is 3 over 2, which is bigger than 1. So the series is infinity. That was. Okay, because r is bigger than 1. Does that make sense? Something like this you might see in the future. A series of 3 times 3n over like 2 to the n minus 1. Okay, something like that, okay? From 0 to infinity. So how to work with this? Actually, I can write here, 3n plus 2, right? Over 2n minus 1. Sorry, here's n plus 1. So n equal to 0 to infinity. You might write like this, you might write, because you need to have the same power, right? So I can write a sum of 9 times 3n minus 1 over 2n minus 1, n from 0 to infinity. And this is 9 sum of 3 over 2 to the n minus 1, n from 0 to infinity. And again, right, if you pay attention on the index, this goes from 0 to infinity. And here, the power is from n minus 1. But it's fine. You may write like this. That is 9 n from 1 to infinity, 3 over 2 n minus 1, and then plus 3 over 2 to negative 1. This is the term for n equal to 0. You see that? So this is a finite number that will not affect the convergence of the series. But this series diverges because, I in this case is 3 over 2, bigger than 1. Does that make sense? Now let's consider some properties of infinite series. And I would say that most of these properties are obvious from the properties of limits. So if you have two series an and bn, and suppose that they are convergent, and the sum of an is a, sum of bn is b, then if you multiply all terms of a by c, so the sum of new series is ca, and if you consider the sum or difference of these two series, you get, a plus minus b. Okay, these properties are true in case two series are convergent. And I have to mention in here, we do not have product rule for series. What does it mean? That means series of an bn is not sum of an times sum of bn, and of course that is not ab. Does that make sense? So this guy product is equal to ab, but this series we don't know about it. Okay, so we try to use correctly. Okay, don't try to make new rules. I often joke to my students like it. Okay, the following is very useful. It's very useful criterion to determine, if a series converges that was. Sometimes this work. Okay, so if sum of an converges, then the limit of an is equal to 0. Okay, as a consequence of this, if the limit of an is not 0, then the series an diverges. So it looks very simple, but sometimes that works really well. Okay, the proof of this theorem is pretty nice and short and easy. You can check that in the textbook. Let's consider a couple of examples. Okay, so let's say series of n over 2n plus 3, and from 1 to infinity. The general term of this series is n over 2n plus 3. And you can see that the general term has limit equal to 1 over 2, right? The limit of an when n approaches infinity equal to limit of n over 2n plus 3, n approaches infinity, and that is limit of n over 2n and infinity, and that is 1 over 2, which is not 0. From here, we do conclusion that our series that was. Okay. Yeah, let's do one more example and then we finish today's lecture. Series 2n over square root of n squared plus 1, and from 1 to infinity. So the general term an is 2n over square root of n squared plus 1. And let's consider the limit of this an at infinity. So you get limit of 2n over square root of n squared plus 1 and approach infinity. And again, we use similarity. We get 2n over square root of n squared and approaches infinity, and you get 2. Right? Again, that is not 0. So the series diverges. But look at this. If the general term has limit equal to 0, this does not mean the series converges. Okay? In this case, yes, the general term is, 1 over n, and the limit of 1 over n is 0, right? When n approaches infinity. But no, this does not imply that the series converges. Please don't forget this. Okay, so when we apply this theorem, some of you may be confused with another implication. If the series converges, the limit of general term is 0. But if the limit of general term is 0, that does not mean the series converges. But if the limit of series is not 0, the series diverges. Okay? So thank you and see you in the next video.